Thank you all. Hi, I am Lin Clark, and I make code cartoons. And I also work with an amazing team at Mozilla. We work on a lot of WebAssembly tools that you might have used, CraneLift, the code generator, WASMtime, the WebAssembly runtime, the Rust WebAssembly toolchain, and more. And we also champion a lot of standards proposals. So one of the earliest ones that we pushed for was actually WebAssembly itself. And since then, we've been championing proposals like interface types and the WebAssembly system interface. So when the organizers asked me to keynote this conference, I had a lot of different topics that I could choose from to talk about. But as I thought about it more, I realized that there was one thing that I really needed to talk about today. And that's a choice that's facing us as a community in this moment. It's a choice that we're going to have to make as we build out this new ecosystem. And that choice is whether we want to use WebAssembly to build a safer future, or whether we want to take a worse is better approach and extend the mistakes of the past. And this choice is facing us now because WebAssembly is moving outside of the web. WebAssembly on the web is portable and secure. The same exact WebAssembly file can run safely across lots of different devices. And that's really appealing, being able to run that same file across all of these different devices. And it's a property that's useful regardless of whether or not you're working on a web app. So people have started experimenting with other ways of using WebAssembly, using it to run server-side tasks or to run code on IoT devices. But as people are bringing WebAssembly outside of the web, they're leaving the browser's sandbox behind. And if that becomes best practice, then we lose one of the major benefits of WebAssembly, its security. We really shouldn't give up on WebAssembly security, because WebAssembly gives us a chance to solve one of tomorrow's biggest security challenges, one that comes from a radical change that's been happening in software development over the past 20 years. 20 years ago, companies had a really hard time getting their developers to reuse code. But now we're building these massively modular applications where 80% of the code base comes from registries like npm or PyPy or crates.io. The problem here is the current software architectures weren't built to keep users safe in this circumstance, and bad guys are taking advantage of that. They're doing that at a dramatically increasing rate, too. What the bad guys are exploiting here is the fact that we're getting our users to trust us. When your user starts up your app, it's kind of like the user's giving you the keys to their house. They're saying, I trust you. But then you invite all of your dependencies, giving each one of those dependencies a full set of keys to that same house. And these dependencies are written by people you don't know and have no reason to trust. More than this, it's not just our own dependencies that come along for the ride, it's also the dependencies of those dependencies, your indirect dependencies. Now, what do all these developers get access to? They get access to resources on the machine, so things like files and memory. And they get access to APIs and syscalls, so tools that they can use to do things with those resources. So this means that these modules can do a lot of damage. This could either be on purpose, as with malicious code, or it could be completely accidentally, as with vulnerable code. Let's look at how these attacks work. First, malicious code. Malicious code is written by the attacker themselves. Attackers often use social engineering to get their package into an application, and they create a package that has a useful feature. And then they sneak in some malicious code after the fact. Once the code is in the app, when the user starts the app, the code can then attack the user. So let's look at how an attack like this unfolds. This is how a hacker stole $1.5 million in cryptocurrency and almost stole $13 million more. On day 0, the attacker published a module to npm. This module was called Electron Native Notify, and it did something useful. It helped Electron apps fire off native notifications in a way that worked across different platforms. It didn't have any malicious code in it yet. The attacker then created a pull request to add their module as a dependency in a dependency of a Bitcoin wallet, and that PR was merged. About 2 weeks later, the attacker added the malicious payload to their own module, to Electron Native Notify. And about a month later, a new version of the app was cut, and that pulled in all of the wallet app's dependencies and all of the dependencies of those dependencies. So that's how Electron Native Notify got into the wallet app. At this point, the malicious code started sending off the seed, the username and password combination for the wallet, to a server. And the attacker could then use the seeds from all of these different wallets to empty those wallets. This went on for about a month or two before anyone figured it out. And in that time, the attacker was able to steal 1.5 million. Let's look at what access this malicious code needed in order to achieve its goal. So it needed a seed. To do this, it got access to the memory that was holding that seed variable. And then it needed to send the seed to a server. For this, it needed access to a socket and access to an API or syscall for opening that socket. So that's how a malicious attacker can pull off one of these kinds of attacks. And these attacks are on the rise, as more and more attackers are realizing how vulnerable our systems of trust are. For example, the number of malicious modules published to NPM more than doubled from 2017 to 2019. And Adam Baldwin, NPM's VP of Security, points out that these attacks are getting more serious. He says, in 2019, we're seeing more financially motivated attacks. Early attacks were focused on shenanigans, deleting some files and trying to steal some credentials. Real basic attacks, kind of smash and grab style. Now end users are the target, and the attackers are trying hard to be patient, to be sneaky, to really have a well-planned out attack. So that's how malicious code wreaks havoc. Now let's look at how exploiting a vulnerability works. Vulnerabilities are different. The module maintainer isn't trying to do anything bad. The module maintainer just has a bug in their code. But attackers can use that bug to convince the code to do something that it shouldn't do. For an example of this, let's look at ZipSlip. ZipSlip is a vulnerability found in many ecosystems: JavaScript, Java, .NET, Go, Ruby, C++, Python, the list goes on. And it affected thousands of projects, including ones from HP, Amazon, Apache, Pivotal, and many more. If a module had this vulnerability, attackers could use it to replace files anywhere in the file system. For example, the attacker could use it to replace JS files in the node modules directory, and then whenever that JS file was required, the attacker's code would run. So how did this work? The attacker would create a file and give it a file name that included a relative file path, which escaped up to a higher level directory. When the vulnerable code unzipped it, it wouldn't sanitize the file name. So that code would call the right syscall with the relative path, placing the file wherever the attacker wanted it to go in that file system. So what access did the vulnerable code need for the attacker to be able to pull this off? It needed access to the directory with the sensitive files, and it also needed access to the right syscall. Just as with malicious code, vulnerabilities like these are on the rise as well. SNCC reported that there's been an 88% increase in these kinds of vulnerabilities across software ecosystems over the past 2 years. With these risks, you would think that patching vulnerabilities would be a high priority. But as SNCC found, only 59% of packages that have known fixes for these kinds of vulnerabilities, because many maintainers don't have the time or the security know-how to actually fix these packages and these vulnerabilities. This leads to widespread vulnerability across the ecosystem as other modules depend on these vulnerable modules. So for example, a study of NPM packages found that 40% of packages depend on code with at least one publicly known vulnerability. These ecosystems have pioneered new ways of working. This new way of working has made us much more efficient as application developers, but they've also opened us and our users up to a whole lot of risk. But this trade-off isn't inevitable. We can learn from these pioneering ecosystems. We can learn from the things that turned out well, and we can also learn from the things that didn't turn out as well. We can create an ecosystem that makes developers productive without giving up on security. To see how, we need to look at where the security problems are coming from. In both examples, both the malicious code example and the vulnerable code, the problem was that these modules had access to things they shouldn't have. What if we took away that access? Now, this seems like a tricky proposition, but we faced this kind of challenge as an industry before, just at a different level of granularity. When you have two programs running on the same computer at the same time, how do you know that one isn't going to mess with the other? Do you have to trust the programs to behave? No, because protection is built into the operating system. The tool that the operating system uses to protect these programs from each other is the process. When you start a program, the OS fires up a new process, and each program gets its own process. Each process has its own chunk of memory to use, and it can't access the memory in the other process. If it wants to get data from the other process, it has to ask for that data. And then the data is sent across the process boundary using inter-process communication, which is basically a pipe between the two processes. For the data to go through the pipe, it has to be serialized on one side and then deserialized on the other. So that adds overhead and complexity. But this does ensure that each program is in control of its own data and memory. Now with this, it's much safer to run two programs at the same time, but this isn't perfect security. A malicious program can still mess with certain other resources, like files in the file system. VMs and containers were developed to fix this problem. They ensure that code that's running inside of a VM or container can't access the file system that's in another container or on the system itself. And with sandboxing, it's possible to take away access to the APIs and syscalls. So could we put each package in its own isolated unit, in its own little sandboxed process? Well, that would solve our problem, but it would introduce a whole other problem. That's because all of these techniques are relatively heavyweight. If we wrap hundreds of packages into their own sandbox process, we'd quickly run out of memory. We'd also make the function calls between the different packages slower and more complicated. But it turns out that WebAssembly gives us new options. WebAssembly can provide the kind of isolation that makes it safe to run untrusted code. We can have an architecture that's like Unix's many small processes and like containers or microservices. But that isolation is much lighter weight, and the communication between them isn't much slower than a regular function call. This means you can use them to wrap a single WebAssembly module instance or a small collection of module instances that want to share things like memory among themselves. Plus, you don't have to give up on the nice programming language affordances, like function signatures and static type checking. So how does this work? How does WebAssembly make it possible to do this? Well, first there's the fact that each WebAssembly module is sandboxed by default. By default, the module doesn't have access to APIs and system calls. If you want the module to be able to interact with anything outside of it, you have to explicitly provide it with that function or with that syscall, and then it can call it. Second, there's a memory model. Unlike a normal binary compiled directly to something like x86, a WebAssembly module doesn't have access to all of the memory that's in its process. It only has access to the chunk of memory that it's been assigned to it. This gives us memory isolation between the two modules. So that means that a malicious module can't mess with the memory of its parent module or any other modules, sibling modules. But how do we share data from our module? Well, you have to do something like pass it in or out as values of a function call. There's a problem here, though. By default, WebAssembly only has a handful of numeric types, which means that you can only pass single digits across. Here's where the third feature comes in, the interface types proposal, which we demoed in August. With interface types, modules can communicate using more complex values, things like strings or sequences or records or variants or nested combinations of all of these. So that makes it easy for two modules to exchange data, but in a way that's secure and fast. The WebAssembly engine can actually do direct copies between the caller and the callee's memory without having to serialize and deserialize the data. And this works even if the two modules aren't compiled from the same language. So with all that, we can isolate the memory between modules without making it too hard to share data. This way we can ensure that a malicious module can't mess with the memory of other modules in the application. But we don't just need to take precautions around how memory is handled. Because if the application is going to be able to do anything with that data, it's going to need to call system APIs or system calls. And those APIs or system calls might have access to shared resources like the file system. So we need APIs and system calls that actually have the concept of permissions baked into them. And this way we can give different modules different permissions to different resources. This is where the fourth feature comes in, WASI, the WebAssembly System Interface. That gives us a way to isolate these different modules from each other and give them fine-grained permissions to particular parts of the system and other resources, and also fine-grained permissions to different system calls. If you've ever heard of capability-based security, that's what this is. So with this, we've taken control of the keys. What's missing? Right now, we don't have a way to pass the keys down through the dependency tree. We need a way for parent modules to give the keys that their children need to those children. So this way, we can propagate those permissions down the dependency tree. That's what we're working on next. In technical terms, we're planning to use a fine-grained form of per-module virtualization. And this is an idea that researchers have proved out in research contexts, and we're excited to apply this to WebAssembly. Taken all together, these features make it possible for us to have similar isolation to that of a process, but with much lower overhead. This pattern of usage is what we're calling a WebAssembly Nano process. It's still just WebAssembly, but it follows a particular pattern. And if we build this pattern into the tools and conventions that we use, we can make third-party code reuse safe in a way that it hasn't been in any other ecosystem to date. With these foundations in place, developers will be able to build dependency trees of isolated packages, each with their own tiny little nano process around them. So how does this help keep users safe? Well, in both of these cases, it's the fact that we're following the principle of least authority that's keeping it secure. So let's walk through how that helps. In order to carry out an attack, a module often needs accesses to resources that it wouldn't otherwise need access to. With our approach, the module has to declare that it needs access to these things, and that makes it easy to see when it's asking for things that it shouldn't be asking for access to. For example, the wallet stealing module needed access to both a socket pointing to a server that was sending the seed to, and a way to open that socket, to open a network connection. But this module was just supposed to take the text that was handed to it and pass it off to the operating system so that the system could display it. Why would the module need to open a connection to a remote server to do that? If Electron Native Notify had asked for those kinds of permissions at the start, that would have been a serious red flag. The maintainers of the dependency that was in that wallet probably wouldn't have accepted it into their own dependency tree. If the malicious maintainer had tried to slip this access request in after having gotten it into the dependency tree, then that would have been a breaking change. The module signature would have changed, and WebAssembly throws an error whenever the calling code doesn't provide the parameters or the imports that a module or function expects. So this means that there's no way to sneak in this access to a new resource or system call under the radar. So it's unlikely that the maintainer could have gotten the basic access that they needed to communicate with that remote server. But even if the maintainer were somehow able to trick the app developer into granting them that access, they still would have had an extremely hard time getting to the seed. That's because the seed would be in another module's memory. There are two ways for a module to get access to something from another module's memory, and neither of them allow that malicious code to be very sneaky about it. Either the module that has the seed exports that as a variable, making it automatically available to all of the other modules in that app, or the module that has the seed passes it directly into that malicious module. And both of these seem incredibly unlikely for a variable that's this sensitive. Now, there is unfortunately one less obvious, less straightforward way that attackers can access another module's memory: side channel attacks like Spectre. If you're architecting your code in a way that protects you from side channel attacks using isolated processes right now, you may still need to do that. Making the shift to Nano processes in that case would take some really careful analysis. But there are lots of situations where timing protection isn't needed or where people aren't using processes right now. And those are good candidates for using the Nano process. So how does this protect users against attackers that are exploiting vulnerabilities? Just as with malicious modules, it's less likely that a vulnerable module actually needs the combination of access rights that the attacker needs in order to carry out their attack. In our zip slip example, even for legitimate uses, the vulnerable module does need access to a dangerous syscall, the write syscall. That allows it to write the files. But it doesn't need access to the known modules directory for any legitimate use. It should only have access to whatever directory zip uploads are supposed to go into. So that would make it impossible for the vulnerable module to carry out the attacker's wishes, unless the parent explicitly passed a very sensitive directory into the vulnerable module. Now, it is possible that an application developer would pass in a sensitive directory like the root directory. But for this to work, that mistake would have to be made at the top-level package. It can't be made in a transitive dependency of the top-level package. By making all of these accesses explicit, it makes it much easier to catch those kinds of sloppy mistakes in review. So that's how WebAssembly could solve this problem. But this kind of security guarantee doesn't just fall out directly from using WebAssembly. As I mentioned before, this is a pattern of usage. The components are all standardized, but following this pattern isn't a requirement to use WebAssembly. If we want to have these security properties, we have to follow this pattern. We have to establish these conventions and bake them into our tools. And that takes some work. As a community, we have a choice. We can choose to fix this growing security issue and make our users secure by default. But if we're going to do this, as we design the pieces of this new ecosystem and figure out how they fit together, we need to bake the security into that design. Because if we don't, WebAssembly could make the problem even more entrenched. We know what future we want to see. We want to stand for the user and fix this problem. And it's a problem that's too big to solve alone. That's why we worked with Fastly, Intel, and Red Hat to form the Bytecode Alliance. Together, we're creating tools built around the Nano process pattern. Then people can use those building blocks to build and run their own applications, whether in the cloud, natively on the desktop, or even on tiny IoT devices. And these runtimes and tooling are built in an opinionated way to be secure by default. So we're baking these conventions into the tools. With this, developers can be as productive as they are today, using open source in the same way, but without putting their users at risk. We're doing all of this because, for us, it's really important that WebAssembly achieves its potential. And we're not the only ones driving this initiative. Others are picking up this banner too and pushing for a new kind of ecosystem, one that doesn't accept the trade-off between developer productivity and user safety, one where we get both. As my teammate and WebAssembly co-creator Luke Wagner said, this is a unique moment in time, at the dawn of a new technology, where we have the opportunity to fix what's broken and build new secure by default foundations for native development that are portable and scalable. But we need to take deliberate cross-industry action to ensure that this happens in the right way. And we hope that you'll join us. Thank you to the organizers for inviting me, and thank you all for listening.